they will tell you more about themselves and they will introduce their reports. So the first speaker will be Saviër. He's lead of public relations at Lunar Zebro, and together with him, you will dive in the Lunar Zebro mission. Saviër, are you here? Can you say hello to our participants?
Yes, thank you. Hello, everyone. Thanks for tuning in for our webinar. My name is Saviër. I'm the lead public relations indeed, and I'm going to give you a small introduction about the Lunar Zebro mission today. Yeah, something about myself. I'm studying aerospace engineering at the TU Delft, and I'm in the Lunar Zebro team for 1.5 years right now. And I can't wait to, in approximately 2 years, be able to point at the moon and say, that's our rover, it's over there.
Thank you so much, Saviër. And when we will dive in the Lunar Zebro mission, after this, when you will learn more about us, we will tell you about building a moon rover and its challenges. Your guide in this part of our webinar will be Ufuktan.
Until then, I will still be lead structures, and I'm that for 1.5 years now. I will tell a bit about the moon rover and the challenges on the moon. That's it. Thank you.
Okay, thank you. I see that participants are joining us. I want to remind you that you can ask the questions to our speakers during all the webinar. You can go to Slido. The link is, we will share the link below the stream. And we are going to next speaker. Next speaker will be Nick, and Nick will tell about the space engineers and team structures. Nick, are you here? Can you say hello to us?
Yes. Hi, everyone. I'm Nicolas. I'm currently the test engineer in the Lunar Zebro team. During my section, I'll talk about how we structure and organize such a space project. And then I will move on to how we're keeping the team morale high during the current global pandemic. And then I'll introduce some of the ways we keep the team motivated when working on a project with deadlines that are so far in the future.
Okay, thank you, Nick. And I want to remind to our participants that we will have a break in the middle of our webinar. And during the break, you can grab some coffee, tea, ask questions using Slido. I want to remind you about this. And after our break, we will go forward, and the next speaker will be Stijn. He will tell you about test missions. Stijn, are you here?
Yeah, hi, I'm Stijn Rovers. I'm 26-year-old, studying space engineering, and I'm currently graduating at the Lunar Zebro team while making the stereo vision obstacle detection system. I'm also chief analog missions, and that's what I'm going to tell you a little bit about later on.
Thank you. We became closer to the moon, and we're going to next speaker. Next speaker will be Claudia. She will give you a nice tour on our office, and she will show you the backstage of creation, the smallest, the world's smallest moon rover. Claudia?
Yes, hi. I'm Claudia, and I'm a second-year bachelor student, industrial design engineering student. And yeah, I'll show you a bit of where we're working. Currently, not so much since COVID-19, but still nice to see where we're doing all this stuff. So yeah.
Thank you so much, Claudia. And I think that online event is a great opportunity to meet with us, because we can pick up each people from a lot of countries and show them our work, how we're working, where we're working, and more. And we are going to next speaker. Next speaker will be Raj Tilak. He will tell you about radio astronomy. Raj, are you here?
Yes, hello, hi there. My name is Raj. I'm an assistant professor at TU Delft. I work on distributed autonomous systems, And I'm going to connect Lunar Zebro with radio astronomy, and how does that look like, and what is the future research prospects? And that's exactly what I'll be discussing about. Thank you.
Okay, thank you. And our next speaker will be Peter from the Netherlands Space Society, main partner of our webinar. Peter, can you tell us more about your report?
Yes, so thank you. I'm glad to be here, and on behalf of the NVR, the Netherlands Space Society, we are very excited to host this webinar together with the Lunar Zebro team. We are very eager to hear about all the work you're doing and the ambitions and the goals you're striving for. I'd like to welcome our NVR members to this webinar, and also the others who maybe not familiar with the Netherlands Space Society. Stick on to the end. I'll let you know a little bit more about what we do and where you can sign up for us. Looking forward to this webinar.
Thank you so much. And yeah, this was our agenda. We did an introduction to our webinar, to our speakers. And I want to remind you that you can ask questions using Slido. We share the link below our stream. And yeah, we will also have a short break in the middle of our webinar. And I think that's all for me. But I give a word to Saviër. He will tell you about the Lunar Zebro. And Saviër, I give you a word. The stage is yours.
Yes, thank you. That's my first slide. I want to start showing you this 90-meter tall building. This is the TU Delft Faculty of Electrical Engineering, Mathematics, and Computer Science. And this is officially the tallest building on the TU Delft campus. And we, as a team, going to the moon, obviously chose this building to have our offices to be the closest to the moon and our goal as possible. So our main offices are located in this building. And within our offices, we obviously have a lot of team members working. We call them the space engineers. We have a really nice international team of multidisciplinary students from bachelor students, master students, PhD candidates, but we also have professors within our team. And we are building this robot. So you registered for our webinar, so I think you already know a little bit that we are building a robot which is going to the moon. And right now I want to give you a small introduction about this robot. And I want to start by going back a little bit and start with this weird name that we have, Lunar Zebro. Where does it stand for exactly? So we have this name, Zebro, and that is actually a Dutch abbreviation for a six-legged robot. And that is exactly what you can see on the pictures and renders of our rover. So on this picture, we have our engineering model of our moon rover. And as you can see, the main characteristics are the 6 legs. And the other main characteristics of the rover that we are building is that it is the smallest and the lightest moon rover yet. So what is so special about this rover, and why is it a Lunar Zebro? Why is it going to the moon exactly? So in front of us right now we have a simple, small and light rover, which is low cost, it is reliable, and it can survive very well on the moon. And the power to the Lunar Zebro, and the reason that we want to introduce this in the moon, is because there is something special going on with these robots. They can work together in a team. And when you have a bigger team, a group of these robots, we have several things going on, like secure communications between the rovers. We have data integrity, and we can distribute our processing, the algorithms, and the decision making between such a group. And you see some of our robots. These are actually our terrestrial versions of the Zebro, all as well with the 6 legs. And you can see them right now in the grass. And we're getting quite close now to where Zebro, our inspiration, where it came from actually. And that is from nature. So let's see. Next slide. Yes. So, oh, that's a bit too far. Yeah. So our inspiration for the Zebro is actually coming from nature. So something very special that we are seeing with insects is that you have very simple units, let's say, which cannot really do that much. But if you put them in a group together, they can perform really special tasks. So they can, ants, for instance, they can build a home together, they can move branches, or they can even, like this frog, for instance, something that is 20, 30 times bigger and heavier than the ant, they can move it together. Um, so that is something really special, and that is the main inspiration we have for our rover. So why do we want to send this rover to the moon? And that's for several reasons. First of all, there's growing scientific and commercial interest in the moon. There are so many missions planned right now. It's moon missions are coming back basically, but it's also for us as a vision from the university to gear up our engineers for the future of space exploration. As you maybe also know, if I'm not mistaken, around 12 years ago, the TU Delft has built a satellite, which is still in operation till today. And we see that building a rover and sending it to a different planet is like a next step in doing projects in space after the nano satellite. And of course, we also want to demonstrate the robot and our future research in swarming for interplanetary exploration. So we want to go to the moon to test it over there and demonstrate it over there. But on the long run, we can use this robot as well on other planets. So, well, a first question that could come up is, how are you going to the moon? So most of the questions coming in normally is, so on what rocket are you flying? So that is something that I want to make clear right now. We're not, so do we already have like a clear launch date? No, we don't. Our rover is really flexible, and we can basically piggyback on any of the public or commercial moon landers. And a moon lander, for example, Alina on the right, that is a moon lander by PT Scientist. And so we don't really use or choose a rocket we fly on. We choose a moon lander, which brings us to the moon. And depending on that moon lander, they will have a rocket on which they will fly, basically. So right now, we're not really, well, not 100% sure on what opportunity we will fly on. We have a certain timeline for our robot, but currently also with the corona crisis, it's a bit unclear which opportunities are shifting and being postponed or which ones are getting closer to our timeline. So that is a really nice thing for us, as we are really flexible. And I think Ufuktan will explain later as well how we are that flexible and why exactly. So we want to go to the moon, and so what do we want to do on the moon exactly? So first of all, we're going to piggyback with a moon lander. And then our main goals over there is to survive a full lunar day, which are 14 days here on Earth. After surviving a full lunar day, our rover will go back into hibernation mode. And then we will hope that it will survive the night. But that is not our main goal right now. Our main goal is to have it running for 14 Earth days or one lunar day on the moon. Furthermore, we want to test our C-shaped legs locomotion on the moon. We also want to communicate directly to Earth. And what would be really nice is to have a rover walk a little bit to the front and actually look back at the moon lander with maybe the Earth in the background and to take a picture. So that would be great. And now we're coming, let's see, to the final of my presentation. And I want to leave you with this video. I think the sound is not working. IT support, is the sound working? Yes. Thanks. Thank you.
I guess it's my turn now. Yeah, I already introduced myself. I still want to say like why I joined this team. And the reason for that it has not been done by students before. So it's a very unique opportunity for students to learn and get hands-on experience with a moon mission and a space mission. It's a very challenging and fun project. Let's see. What's also very challenging is the lunar environment for the rover. It has extreme temperature from minus 233 Celsius to 123 degrees Celsius. These are the temperature extremes, but the average temperatures are around minus 153 for a moon night and 107 degrees for a moon day. And a moon day takes approximately 14 days on Earth. Our thermal system should be able to handle these extreme temperatures, and we should increase the operational time on the lunar surface. The lunar surface does not have an atmosphere. That means there's vacuum, and ionizing radiation will come through it. There are different kinds of ionizing radiation. There's galactic cosmic rays, solar wind, solar flare. These are all harmful for the rover's service of the materials and also for the electronics. It can cause failure. and we should be able to protect our electronics inside of the rover from this harmful radiation. Furthermore, the gravity on the moon is not the same as the gravity on Earth. It's 1/6 of the Earth's gravity. It's 1.62, and the locomotion design should be based on that one. And we can test it with helium balloons on a rough surface and create and simulate this gravity, so that we are able to walk on this on the lunar surface. And then we have the trafficability. That actually means, let's say we have a human walking on the sand. That's not the same as a human walking on the sidewalks. The legs of the rover are designed in such a way that we are able to walk on this dust on the lunar surface. Like, okay, I already said about the moon dust. The moon dust is very sharp and very abrasive. This can also cause harm to the electronics and also to the mechanical components. So we should be able to protect our components from this harmful lunar dust. Furthermore, it's also electrostatically charged. That means that it sticks to all kinds of components and to non-conductive surfaces. No, sorry, non-grounded conductive surfaces. There's also rough terrain on the moon. We have craters, we have obstacles. As I said, we have moon dust. We should be able to walk on this rough terrain, and we should be able to navigate through this terrain. And how we will do that, I will explain in a bit. I already touched upon the ultra vacuum, so there's no atmosphere causing the radiation and also the temperature to be different than on Earth. There are also different factors for that. And then finally, we have the micrometeorites, which are very small particles from less than 1 millimeters. And they're traveling so fast, like 13 to 18 kilometers per second, that it can still cause harm to the rover. And we should be able to still function after a hit of the micrometeorite. So we need to analyze our rover and see if it can survive, and how we can make it how we can make it such a way that it can survive. Then we have the design of the Lunar Zebro. Here you can see the 6 C-shaped legs on the sides. These are so the reason we have 6 is it's very stable. If you have let's say if you have a slab and it's another slab, it's always resting on 3 points. And that's the same with the rover when it's walking. We always have 3 resting points that increase the stability on the rough surface on the moon. And the legs are being able to turn in both directions, so it can go both forward and backward. And it can also turn sideways in both left and right. So we are really flexible in our locomotion. Furthermore, it can go over its own height. That's very special. Wheels cannot do that, but our rover can walk in such a way that it can go over its own height. And this gives us additional benefits. We can go over obstacles of lower than its height. And the chassis is made out of aluminum 7075, and all the electronics are in the chassis itself. It provides protection to the subsystem inside, and it hosts the subsystems. In left, you can see, like left under, you can see fungible, and that's a weird thing, but that helps the rover to deploy from the lander after the long journey from Earth to the moon. This thing will help deploy the lander so that it can operate on the moon's surface. Then we have shrimp. That's the abbreviation is Small High Resolution Independent Modular Photographer. It is built by students from TU Delft, and we have 2 of them in front of the rover. And this will help us to navigate through the terrain and detect obstacles and avoid them. Then we have the solar panel, and the solar panel hosts 12 solar cells, which will help us to power the rover. And we have the solar panel deployment system, which will help to deploy the solar panel from 0 to 90 degrees, depending on the solar rays coming, touching the solar panel. And then you can see an antenna sticking out, and the antenna is always kept 90 degrees to the rover itself, so that it can maintain good communication with Earth. And I think that's it from my side. Oh, sorry, I forgot one slide. We also have LEAP. This is another component we are working on. This is a different section than the rover itself. Different team is working on it as well. Basically, we want to send this first to the moon before sending the rover, so that we can demonstrate our camera shrimp and demonstrate our communications module. It's a very basic and passive component. We will stick it on the lander itself, and it can communicate with Earth, and we can, before sending the larger rover, we already have a good operational knowledge of a moon mission. This will help us indeed with the rover. Then I would like to invite Nick for his part.
All right, thanks, Ufuk. All right, hey everyone, I'm Nick, and once again, I'll briefly go through what I'm going to be talking about in my presentation. So first, I'll talk to you about how you split a group of 50 people into smaller, more manageable teams, and then go on to what some of the roles in each team are. After this, I'll talk a bit about how we are continuing to do our work and staying on track during the COVID-19 crisis and keeping the team morale high. And then finally, I'll introduce some of the ways we're keeping the team motivated when working on a project with deadlines that are so far in the future. So let's start with the project division. Here are 2 pictures of the Zebro, both taken during the assembly of the engineering model. There are some notable differences between the state of the Zebro in both images, which will help us figure out how we can divide up the project. On the left, we can see more of the physical skeleton of the Zebro. Oops, I can't seem to control. Okay. You can see the physical skeleton of the Zebro, which includes the legs and the chassis, which can be seen there. These we can group into having a certain physical appearance, design, and material. The people that work on these things, we can group into a team called structures. Now, on the image on the right, we can see more of the inside of the Zebro, essentially the guts. You can see cables and connectors inside wiring together electrical components, such as the batteries and sensors. Everyone that works on these things, we can group into a team called electronics. But what we can't see in these pictures is how we control the Zebro, how the sensors actually read the data, and how the communications data is handled. These are all controlled with code, and someone has to write this code. So we will call this group software. These 3 groups, so structures, electronics, and software, need to work together well and coherently, and they need to follow certain design rules, requirements, and specifications. The group that will ensure these sorts of things are followed can be made into a team called operations. So now that we have the 3 design teams and 1 operations team, we are ready to share our design of the world. talk to partners, and inspire some new members, we need a public relations team. And then finally, we need people that will keep the project on track and give us the goals of the project. We need a management team. So that's it. Those are the 6 teams that we as Lunar Zebro and many other companies have decided to split our group into. So now let's move into some of the more specific roles of each group. So firstly, structures. The most immediate and most obvious role is the physical design of the Zebro, such as the shape of the legs, the shape of this chassis, the nuts and bolts which hold everything together. The mechanical engineers are the ones in charge of this, and therefore work very closely with computer-aided design engineers. These CAD engineers are in charge of the 3D model of the Zebro, and any and every component that goes into it. They assemble all of them virtually. This is very important when visualizing the design and for team communications, production, design iteration, and simulations. These simulations are performed by the simulation engineers, which you can see on the left, who have a very important task as they let us test the design without physically having to test the design. Now I'll say it now, but this applies for all the other teams that I'll be talking through. These are not the only roles that the structures team has. If I were to talk about every single one, we would be here for hours. So I'm just highlighting 2 or 3 from each team. We can now move on to electronics. The most obvious role within electronics is the power. As a student team, it's quite difficult getting our hands on nuclear energy sources, or RTGs, so instead we're going with batteries. What would also be great is if we could generate our own power. So therefore, the Zebro will have the solar panel, which can charge up the Zebro, and it can be self-sufficient. Furthermore, in electronics, we also have all the sensors on board. For example, the cameras, shrimp, which you can see in the middle picture. All of these sensors need to be controlled by software. So therefore, we can now move nicely onto the software team. We've been assuming that the Zebro understands all of our commands and knows how to walk. But without the proper software, the Zebro is essentially a very expensive brick. Within software, there are the software engineers who are in charge of multiple applications within the Zebro. To list a few are the DX, also known as the diagnostics, the PPU, which is the power processing unit, the BMS, the battery management system, Shrimp, which is the camera, which we saw earlier, the locomotion, which is the software to make the 6 legs work together, which make the Zebro walk, OPAL, which is the obstacle avoidance software, there's the payload, there's comms, which is the communications, and finally we have Tron, which is the main brain of the Zebro, which controls all of the software. So, as I said earlier, we need a team to make these other 3 teams work efficiently and work together. We called this team operations. Now, within operations, there is a very important background role, which is the ground station. This is essentially how we will talk to the Zebro when it's on the moon. On top of our office, which you can see on the image on the left, is a ground station built to control the miniature university CubeSats. This works great. However, the moon is many magnitudes further away than these satellites, so we need bigger antennas. Luckily, here in the Netherlands, we have a 25-meter diameter dish at Dwingelo, which we have been very fortunate to have been given permission to use. And we're also working on an array of similar antennas all around the world, which will give us 24/7 contact with the Zebro. So moving on, we have the people that make the other teams work well together. They write up the requirements and tasks and keep the project moving in the right direction. This role within operations is called systems engineering and is very important. Next, we have the PR team, or public relations. They have lots of roles within the project as well, such as communications with the public. Here on the image on the far left, you can see Saviër and Claudia talking to a local radio station about the project. PR are also in charge of getting the team invited to and attending special events, such as the European Space Agency Open Day, or our very own Aerospace Faculty Space Symposium. These sorts of events are very important as they let us meet all sorts of people, from inspiring younger generations to connecting with highly experienced and professional space engineers. They also let other students find out about the project, so that we can recruit them if they're interested. Within PR, there are also the team events, such as movie nights, game nights, or dinners. These are important in keeping the team morale high, and I'll talk a bit more about these in a bit. And finally, we have the management. They are the backbone of the project and really cement any work and progress that is made. They're the ones who ensure that the bigger picture of the mission is still on track and get us in touch with specialists who may want to join the team as partners. They are also in charge of creating and maintaining the project budget, making sure we don't spend too much money. So now I will be completely honest with you. The way I have just described how the team is organized has been the way we have done it the past 2 years, but it's going to be a little outdated in just 2 weeks. At the start of August, we're having a shift in the organization of the team. Having the 3 design teams was incredibly useful when in the design phase, but it's actually more useful to move towards a more subsystem-based structure, where each member works on their subsystem with their other teammates. I'll quickly go through the different subsystems teams that we'll be dividing the project into. We have the communications team, the command and data handling team, the locomotion team, the payload team, navigations team, chassis team, the power team, and then the ground station team. So for example, if we just look at the locomotion team, we know that it's comprised of the software to control the leg motors, the power or electronics to actually drive the motors, and then the physical structure of the leg. So as you can see, there are 3 members from the original 3 design teams working together on one single subsystem. The original 3 teams will still exist, however, the main work and decisions will be made in these new smaller subsystem-based teams. So each subsystem team will have their own dedicated systems engineer, who's going to work closely with a new role in the team, the chief engineer, who in turn works closely with the entire subsystem engineering core, who work directly with the project management. So that's how the team is currently structured and how we'll be moving forward with the organization as we enter a new phase of the project. However, we have run into a pretty interesting dilemma over the past few months. As per government rules, the majority of the team cannot access our offices or facilities. We have run into the corona crisis, or not really a crisis. We as a team are trying our best to keep on schedule. Every week, each team has their own meetings. The team leads also meet up every week. We're still recruiting and hiring new members over Skype. In fact, our newest batch of systems engineers were hired the same week that the university had to close. So they've never worked from inside our offices, but they already feel like valued members of our team. There are even some new members in the structures team and also in public relations, for example, Katya. Our PR team is also always organizing events to keep our team morale high. Before Corona, we had movie nights and Christmas dinners, but during Corona, there were some Zoom calls just to hang out and chill and talk to some of the group members, as you can see on the left. And now, hopefully, once all of this is over, we can all meet up again and go have some nice barbecues down at the lake in Delft. Now, finally, I'm going to talk about the motivation of the project and how we keep our members working and interested in the task, even though the final goal is so many years in the future. Well, we have to have smaller milestones along the way, such as... I'll talk a little bit more about that in a second. But the smaller milestones, such as the LEAP project. Ufuk has already gone through the LEAP project with you, but it essentially gives members practice and experience working on a smaller project, where all this experience gained can be directly implemented into the Lunar Zebro rover. This project is hopefully going to take place before the actual Lunar Zebro, so therefore there's a smaller milestone to work towards before you get to the bigger goal. We're also involved with external teams, such as the Euromoon Mars team, who are working on joint human and robotic surface operations, where we can provide some Zebros and in return get some valuable data on the effectiveness of the Zebros on other planetary surfaces. The next speaker, Stijn, will talk to you more about this. But for me personally, the biggest motivator is just looking up at the moon in a clear sky and thinking one day our work is going to be up there. Thank you for listening to my section about the Lunar Zebro. I hope you found it interesting. I'm going to pass you back over to our host, Katya.
Thank you, Nick, so much for your presentation. Right now, we are going for a little break, for 15 minutes, but in this time you have a lot of opportunities to spend this time useful. You can grab the tea or grab coffee or go to our website to look at our open position, or go to Slido. You can ask questions, and also we have a poll about our webinar. Your feedback is really important for us. So yes, you can do these things, and we will come back in 15 minutes. We will come back at 4 p.m. And see you soon. Please don't leave our stream. We will come back soon, and we will dive you deeper in our project. And what's the sounds? Hello, everyone. We are happy to back after our break. Hope you are grab your coffee, tea, ask a question, or you applied to our open position. Who knows? But we're happy to have you back, and we continue to trying to reach the moon together with you. And our next speaker will be Stijn. He will tell you about test missions, and yeah, we will continue to reaching the moon together. Okay, Stijn, are you here?
Yeah, welcome back, everybody. My name is Stijn Rovers. I'm Chief Engineer Analog Missions in the team, and I'm gonna tell a little bit more about analog testing. So let me first start with what is analog testing. For us, it means that we are simulating moon conditions on Earth to test various subsystems and team dynamics. And what subsystems can you think of? That are the following. You can think of locomotion, where during the analog test you can quantify walkable terrain and obstacles, and also test different walking behaviors with different configurations. You can also test navigation by gathering vision data, and you can enhance team dynamics by practicing operation control, and majorize the software in the rover by training test teleoperation modes and autonomous modes. To make this happen, a prototype needs to be made. It needs to be designed and manufactured, and during this design and manufacturing, every discipline of the team comes back, like the structure, electronics, and the software. To make a successful test mission, things as
as having a test plan and test protocols are critical, as well as being prepared for the worst case. So having enough spare parts, along with making sure that the rover really is working while being at the test site. Last January, we got in contact with the Euromoon Mars team. They asked us, can we have a rover, basically? And we made it happen by sending them an ancestor of ours. And this was, the Euromoon Mars group is a group that is performing analog missions under the flag of ESA. And they tested for us locomotion on Hawaii, on the volcano there. And they tested it on flat surfaces. But also on a bit more complicated surfaces, like here. And it tests also some robot cooperation.
Okay, cool. Yeah, that's good.
So this summer we had the opportunity to join the Euromoon Mars team to go to Iceland and Italy, but due to COVID-19, unfortunately, this was cancelled. The Iceland mission itself was, they planned to build a habitat outside and inside the lava tube, where we could also test our rover. And during the Etna campaign, we could test at the Etna volcano in Italy, where DLR and ESA had a big mission, and we could piggyback that mission. The mission, by the way, called Arches. So due to COVID-19, this all went by, these opportunities went by, but we still wanted to test somewhere, and then we find an opportunity in the Netherlands. Also, due to the Euromoon Mars team pointing out this location, and we found a Mars yard, DCOS, the company DCOS. And then we tested there the Zebro, again the Desi Zebro, the ancestor of the Lunar Zebro, and we implemented the stereo pi, so it had stereo vision on board, and we tested some locomotion and gathered some stereo vision data there. And here you could see some stereo vision data of the inside the rover. But unfortunately, this all was with the Desi Zebro, and during Corona, I pushed a lot to make sure we've got this working with a test Lunar Zebro. And last week, we finally made this. We finished this model, and it's now walking. We have a stereo vision walking test rover with new modified hardware in it, yeah, you can see it. And with this test rover, we want to compete during Igluna. Here it is. Yeah, Igluna 2021. We applied for this. We're not sure if we're in, but the Igluna mission is on top of the Mount Pilatus, where we want to send a Zebro, a swarm of Zebros, which are going to be operated from a city at sea level. Yeah, these are the projects we work on at the moment. But let's show us to you the space where we work.
Yeah. I see that we're ready for the tour. So yes, indeed. Right now there aren't many people here at the office due to COVID-19, but there have been some space engineers here working on several aspects of not only the rover, but of course the analog missions that we will be doing next year. So this is the software team, and here is Stijn. I just did the presentation for you. And I'm also here with my cameraman, Saviër.
Let's try. See.
Yeah.
Hello.
Yeah, and here we have some stuff on the table. Here we have, for example, the chassis of the Lunar Zebro itself, a bit dismantled. And here we have a couple of terrestrial Zebros that we're not doing much with right now since we have finalized the 3D printed Zebro for the analog missions. And here is another nice little wall that I personally like, which is our previous members. Rest in peace, all of our ex-members. You will be remembered. And then we're gonna continue down the hall. Bye, Stijn. Okay, so now we are on the 18th floor of the 80 building. So we're pretty high up in the sky. Here you can see the number 18 on the floor.
Yep.
All right. And if we move along here, gotta move a bit more to get to the next office. Here we have the project headquarters and operations center, but we won't be going in there today because it's a bit classified, our work in there. And here is where we get our tea and coffee. So here's sometimes we would take a break from work. Before the COVID-19 situation, we would usually work at nighttime. So usually our school or our university work would end at 5:50, and at least I would directly come here and work with the team. And after we have a break, we come here and have a chat. So yeah. Now if we come this way. And here we see our team wall with all our members. And as you can see, there are a bunch of question marks here. Why? Well, the school year is ending, so there are a lot of people graduating right now, and they will be leaving the team. So we are actually looking for new people. So if you happen to be interested, or you know someone who lives in Delft and attends at TU Delft, then they could consider joining. And you can check out our open positions on our website, zebro.space. Yes, now let's continue. Now, as I said, we are on the 18th floor, and this is our view. I'm not sure if it can be seen on the camera. And yeah, over there, yeah, you probably can't see it so well, but that's actually the city center of Delft with its two churches. So that's nice. And now we are going into the next office, which is the Assembly and Integration Center. Okay. And here we have our other speaker, Ufuktan. Say hi.
Hello.
And if we come in here, in this room we basically have all our tools for the assembly and integration of the rover and other things. Yeah. Cool. Bye.
3D.
Oh yeah, we have a nice 3D printer here too. And now we go to the next office. We do have our electrical department office downstairs on the 3rd floor, but we won't be going there now. But right now we will be going into the structures and thermal center. And yeah, so this is the structures department office. Here I also work as a CAD engineer. And yeah, I personally quite like the decoration we have in there. We also have a nice Christmas tree. Yeah. And yeah, so this is where we do things. And now we're gonna go back down the hall again to our next speaker. Okay, you got anything to add, Mr. Cameraman?
Not really. I think it's quite complete.
Okay, cool. These are the elevators.
Elevators.
They're really fast. Kind of makes you dizzy, but you get used to it. And here we have our speaker Raj.
Standing.
Hello, everyone. Yes. And
My office.
yeah, and we will be talking about something that goes beyond Lunar Zebro. So I will give it to you.
Thank you. Thanks a lot.
Yes.
Thank you.
Bye.
Well, hello everyone, and I hope you enjoyed Lunar Zebro's presentations and the tour of our floor. My name is Raj, and I'm an assistant professor with the Faculty of Electrical Engineering in TU Delft, and I work heavily on distributed autonomous sensor systems. And today I'm going to talk about a little bit beyond what we do with Lunar Zebro. What are the other systems that we work on, and what are the research activities that we perform at master's and PhD's levels, right? So that's at a higher level. And how does that all that story connect to Lunar Zebro, right? And that's pretty much the overview of my presentation. So before I go into the presentation today, a little bit about me. I'm a professor, so obviously I do a little bit of teaching. I teach estimation detection theory, which is essentially machine learning with some statistical flavors. I teach systems engineering, and we have a beautiful course on autonomous driving at the bachelor's level. My key focus area in terms of research is navigation, distributed algorithms, and space-based interferometry, right? But the most exciting thing for me on a day-to-day basis are the projects that I work on and the students I encounter in these projects. Of course, I stand in front of you today as the advisor of Lunar Zebro team, as you got exposed to this afternoon. In addition to rovers, I'm also involved in drones. And so I am a work package lead on autonomous navigation for drones. It's an EU project where we work on how to navigate a drone autonomously and cooperatively with other drones. And the third project, which I'm a technical coordinator of, is the OLFA consortium. And that's a consortium of over 15 universities, organizations, and institutes, research institutes, which work heavily on breakthrough technologies for space-based interferometry. And today's talk, I hope I can convince you that some of the key technologies that you would see in rovers, in drones, and satellites are pretty much identical. If not identical, they're fundamentally the same challenges that we face at a lower TRL level. But before going into that, I would like to motivate the need for space-based radio astronomy, right? So if you see to the right-hand corner of your presentation, so you see these bunch of satellites having lines between them. Essentially, that is just to illustrate the fact that they do interferometry. And the reason they do interferometry is to observe in the radio wavelengths, right? So why do we need to observe in the radio wavelengths? I'll start with that. And then hopefully at the end of the presentation, I can convince you that some of the key research areas that we work on are focused in tackling all these three challenges, be that for satellites, rovers, or drones, right? If you look up in the night sky, this is how the sky looks in the optical spectrum. And this is our Milky Way, of course. And but this is just in the optical spectrum, and we can look in the cosmos in multiple wavelengths. And this is just an example of some of the most popular images that we see, be that in X-ray and gamma ray and in ultraviolet. But the most interesting thing for me in this presentation are the radio spectrums. So that's the bottom right two images on your screen. The Dickey map of 1420 megahertz, where the hydrogen transition occurs, and the Haslam map of 408 megahertz. Now, all these maps are mostly made on Earth, right? So the radio maps especially are made on Earth, and they give really interesting insights into various aspects of the functioning of the cosmos. But especially in the radio spectrum, we can actually understand the origins of the universe, and it tackles a lot of unanswered questions for many decades, right? So these span in cosmology, extragalactic surveys, and transients. And there are really interesting signs at ultra long wavelengths, which is 30 megahertz or 10 meters or above, right? And one of the successes at these wavelengths for radio waves especially is just clearly illustrated in this map. What you see on the x-axis is wavelengths, what you see on the y-axis is atmospheric opacity. And the lines basically just show this amount of opacity across these wavelengths. And if you look at radio waves, they're really clearly visible on Earth in comparison to other wavelengths, which are severely restricted. A great example is the visible light itself, which, as you know, if you have clouds in the sky, you won't be able to see farther away. And it's one of the reasons for optical spectrum observations, you have to go on top of the mountain, right? So really high altitudes, like this is Mauna Kea Optical Telescope is one of the best optical telescopes on Earth in Hawaii. Unlike this, we don't have to do this. In radio astronomy, you can be on Earth and still have a clear view of the sky in the radio wavelengths. And so how do we do this? We use a lot of dishes. This is an example of a very large array in the US. This is an example of GMRT, the Giant Meter Wave Radio Telescope in India, the meter wavelength array in Australia, and last but not the least, in Netherlands, we have the LOFAR. These are multiple antennas separated at a certain distance, synthesizing an aperture or a dish which is as big as the farthest antennas in that cluster, right? So, and using these sensors or detectors or antennas, what we are able to see is a spectrum somewhere between 50 megahertz and 50 gigahertz. And one of the things that you notice is all these arrays, radio arrays, are limited at the lower end around 50 megahertz, right? And why are they limited? And it comes back to the same image that I showed you earlier. What happens beyond 10 meters on the right-hand side of your of the axis is that the atmosphere becomes opaque again, right? So, and there is atmospheric opacity, but during this transition between 10 meters to longer wavelengths, you also have ionospheric distortion, and you also have solar flares. Not last but not the least, man-made interference also occurs below 30 megahertz. If there are electrical engineering and communication students out there, we have our AM bands, right? So, and then we also have a lot of other interferences from other communication spectrums. In fact, our man-made interference is so large that you can actually, so high, not large, but high, that you can actually hear it far away from Earth. And this is shown in this plot. This is a plot taken by RAE Explorer, which many decades ago. The satellite was orbiting the moon. And on the x-axis, you see the universal time coordinates. On the y-axis, you see the antenna temperature, which is indicative of sensitivity. And as soon as it went behind the moon, you can see 2 orders of magnitude reduction in the antenna temperature and sensitivity, right? So sort of goes to show how much interference we have. And another experiment was the ESA study, the WON study of 1997, where you sort of could detect the amount of interference as we move away from Earth. So the 3 graphs are at 40 Earth radii, 93 Earth radii, and 157 Earth radii. And as we move away from Earth, we can see at these long wavelengths below 30 megahertz, the interference reduces, right? So essentially what you have to do is go away from Earth so that we can detect these radio waves, which we receive from the cosmos very clearly, right? And just to put it even more bluntly, some of the best maps that we have in the radio spectrum from Earth obviously at higher frequencies, let's say the Haslam map looks like this. And this is at 408 megahertz, and 3 telescopes were used to make this beautiful map in the 80s. If I were to get the best map at ultra long wavelengths, that is below 30 megahertz, this is what it looks like. So it's essentially a contour map, as you can see, right? So it's a contour map of 4.7 megahertz, which was taken by the lunar orbiter RA2, somewhere in the late 70s, right? So the solution is simple. We must go to moon. And why moon? Because it's far away from where we are, and the moon far side gives us a lot of protection from man-made interference and solar flares and other kinds of interference. It's right. Excellent. So what next? Well, the OLFA-PIP consortium essentially is working on fundamental challenges to tackle this problem. So obviously going to the moon with multiple satellites is not a one-day or a one-man show. So we work with 15 plus research institutes, universities, and industries. And there are over 6 postdocs and PhDs, which work on 6 key aspects of the OLFA network, right, or this challenge. One of them is antenna systems. You need antennas for science detection, for intersatellite links and Earth downlink. You also need communication. You need effective intersatellite communication. Each satellite will have its own science antenna. You want to communicate that data. And once that data is communicated and processed, you want to downlink them to Earth. Handling one satellite itself is a challenge. And on top of that, mission planning for multiple satellites so as to get the best out of science is a systems engineering challenge. And the design and implementation of these space systems is also something that's addressed by TU Delft, specifically at the aerospace faculty. We work heavily on navigation, autonomous navigation, GPS-denied navigation, and cooperative attitude and estimation and control. And last but not the least, the control autonomy and the distributed computing aspects. So we have an array of satellites which should go around the moon and look in the radio spectrum. And so if we have to do this efficiently, distributed computing is the only way to go about it. And so distributed correlators is essentially to process the science data, whereas distributed communication, navigation, control will be supporting structure for the other subsystems. So in all these aspects, if you closely observe, except for the systems engineering part for satellites, other challenges are equally applicable to both rovers and drones, both terrestrial and on-moon. So it is one of the reasons why we tackle these challenges. And although they look far-fetched for OLFAR itself, they're very immediate for Lunar Zebro and also for drones in Atacorsa. All right. So that's pretty much the plan we have. And the next question is, how does this all fit in? And so we have a roadmap, it's a tentative roadmap, and we call this the OLFAR roadmap, the Orbiting Low Frequency Array roadmap. And as of 2019, 2020, Netherlands has an antenna on the far side of the moon, behind the moon, Lagrange. It's called NCLE. Terrestrially, we are working on testing our miniaturized electronics, communication and navigation systems on balloon flights. And that's the first phase that we are in. The phase 2 is going to be a multiple satellites orbiting Earth. There are at least 2 projects that I know of which are currently working, project teams that I know of in our consortium, which are working day and night to ensure a testing of these systems. And the phase 3 is where Lunar Zebro comes in, and hopefully by 2025, if not one, we can have more Lunar Zebros on the far side to do radio astronomy. And last but not the least, we have our old far dream of in the coming decade or two to have a cluster of satellites orbiting the moon, doing science on the far side, and communicating the data back on the near side. Right. Well, thank you for your attention, and I hope you have questions for me. And that ends my presentation. Thank you. The floor is yours. Thanks.
Thank you, Raj, for the very nice presentation. Hope everyone can hear me fine. My name is Peter. I'm a former aerospace student from TU Delft Aerospace Engineering. It's some while back, but the space bug is still within me, and I'm happy to contribute to the Netherlands Space Society as a member of the board and activity coordinator, and I'm very happy to host this webinar today together with the Lunar Zebro team, and it's fantastic to hear on the rover that they're working on, how far they are proceeding, know a little bit more on what these guys are up to, and I think it's fantastic. So very happy. I think you can also express this on behalf of the NVR board that we are doing this together today. So we should have a good number of NVR members today. So for them, this will be not new information, but to those who are attending who are not familiar with the Netherlands Space Society, let me give you a brief introduction of what we are and what we do, and why we hope that you will join us to join this kind of events in the future that we organize on a regular basis. So let's see, slides are working. They are not. There you are. So who are we? We are a society that was founded almost 70 years ago. We have big celebrations next year. And we have corporate members and individual members. And we want to promote space to those members, but also on a broader sense to the Dutch public. And we are a community based of space professionals, future space professionals that we see working very hard on very nice projects this day with the Lunar Zebro team as a very nice example of how future space professionals are already active in the field. And last but not least, we have our enthusiasts. We have over 1,200 members, and we promote the Netherlands space flights, but also the international space flight to our members and amongst the companies as well. We have over 25 corporate members, companies, institutes, universities that have joined us, and this community is growing continuously. So what we do is, and this one goes way back to the beginning, is that we have our magazine that appears 4 times a year. It focuses on current projects, future projects, space-related activities from Dutch companies, international activities. And we publish this in a hard copy and a digital copy, and you'll find a mixture of Dutch and English articles in it. And besides our magazine, we, hang on. Just a second here. See if I can go back to my presentation. Unfortunately, there are some slides missing, so I'll have to fill in the gaps with what I can tell you. So we have a magazine that you will receive 4 times a year. But in addition to that, we organize on average 2 events per month. Currently, we focus on online events, webinars. This is one of the examples, but we have the next one coming up in a few weeks. Also partnering with the National Space Museum at Lelystad. And once the measures for COVID are a little bit more released again, we want to go back to our regular visits of companies, movie nights with documentaries, the lecture nights that we organize regarding specific topics on current events or history or future. These events also are great opportunities to network with the members. You will find professionals coming in enthusiast, I can vouch for myself that it's a great platform to establish a great network, scouting for opportunities. So if you will become a member, and unfortunately I cannot show it here on the slide, but go to www.ruimtevaart-nvr.nl, and I'll say if we can, can show the website link another way, but go to our website, ruimtevaart-nvr.nl, and you'll find a way to become a member of our society, and we look forward to welcome you and see you in our future events. And with that, I'll give the floor back to Katya to run the Q&A of today's fantastic webinar.
Thank you so much for your presentation, Peter. And I want to invite all speakers. Please turn on your video and your sound. We are going to answer the questions. Yeah, we did a great job. We almost reached the moon. And I think the last step of this webinar is a Q&A session. And we collect a lot of questions. By the way, you can also ask questions on Slido, and you can also pass our poll about our webinar, give us some feedback, and we will give you more content. Okay, I will start to read the questions. The first questions I see is, what is the payload of the rover? Who can answer? I think that Nick can do this.
Yes. So the Lunar Zebro is quite special in that it's a modular design. So we're not limited to any specific payload. So depending on the mission, we can change the payload. But for the first mission, we're actually sending some radiation sensors inside the Zebro so that we can characterize the radiation on the surface of the moon and measure the total ionizing dose, which is quite important because it's never been done on the surface of the moon. It's only been taken, the measurements have been taken from orbit, so no one's ever actually measured the radiation from the surface. And this is important for colonization of the moon or future missions in testing of other missions of Zebros and other things. So yeah, the first one is radiation.
Okay, thank you so much for your answer. The next question is, if the rover topples, lands on its back, can it land on its feet, legs again? I think that Ufuktan can answer this question.
Yes, thank you. I like this question, by the way. We thought about this. There are two ways you can do this. Yeah, a third if you're not able to do it, but two ways are, one, you can use the locomotion, so the 6 legs, to kick the rover back to its original state. The second way is we have a solar panel, which can deploy from 0 to 90 degrees, we said. And by changing the gravity, so center of gravity, you will be able to topple. However, we still need to test this, but we definitely want, if it lands on its back, that it can go back to its feet.
Thank you so much for your answer. The next question we got from Slido. I remind you that you still have the opportunity to ask a question, and we will answer. And the next question is, what are the approximate cost of the hardware BOM? I think that Saviër can answer this question.
Yes. So the approximate cost of the hardware, or the bill of materials, basically. So it's nice that we're referring to the bill of materials here, because that is actually currently we're relying a lot on our partners. We're working a lot with our partners and together with the TU Delft, of course. So most of our sponsorships are actually in kind. So we try to get our materials, like our legs, for instance, or the main material of the rover. We try to get that through our partners. So currently, it's quite difficult to give an approximate cost of the hardware exactly, but we can very easily say that it is much cheaper than any traditional or conventional rover, let's say.
Okay, thank you, Saviër, so much for your answer. And I see that we missed one of the first questions. This question is, if you use Dwingilo parabolic antenna, you will only have a part-time communication. It sounds like a really hard question, I think. Nick, are you here? Can you answer this question?
Yes, so they're correct. If we only use Dwingelo's antenna, then we'll only have part-time communication. So that's why we're actually communicating with lots of other companies and teams who control and maintain dishes all around the world, such as in India and Australia and the USA. And by having these spread out all across the world, we can actually have 24/7 communication. So we're not just using Dwingelo.
Thank you. Thank you so much for your answer. And the next question is, how far do you expect to walk on the moon? Saviër, can you make small...
Yeah, that's an interesting question. So our mission is actually, so it's in cycles. So we are on a power budget, and that means that we can walk for a bit, and sometimes we just need to sit down for a bit and charge up our rover. So the charge cycle is around, well, the walking cycle, so the rover can independently work for 30 minutes, and it can go with a speed of 1 centimeter per second. So if you make the calculation, you will have 1.8, almost 2 kilometers per cycle of 30 minutes.
Thank you for your answer, but don't leave, because from the moon we are going to Mars, and next question is, will you try to go to Mars next?
Interesting question. So currently our main goal in Lunar Zebro, let's yeah, get that straight right now. It's to get one rover on the moon to demonstrate the platform that we have. So some people could, I think I also saw some questions about, are we planning to send the swarms to the moon already or something like that? So the swarming technology is something that we can test here on Earth with multiple zebros. I've shown the picture during my presentation of multiple terrestrial zebros walking around actually in the garden at our offices, and also here in the park of the TU Delft campus. And to test the swarming, we don't necessarily have to go to the moon, but to test our rover itself, and actually the biggest challenges is to have a working rover this small and this light on the moon. So that is our main priority right now. And then that means that we have demonstrated the platform. And what happens next is, that is to the university, but also to the industry, what to do with such a platform. I think maybe Chris, can you add something to this question?
Yes. What I would like to add is that this question makes me remember of discussions we had when we were building Delta C3, our nano satellite. Before it was launched, people thought it as it was instant space debris and useless and so on. And then with people like Wim Jonkind and Rob Hamann, we were talking that after it's launched and it works, the world will be different. And indeed, it was different, because once it was flying there and working, and by the way, still working, the nanosatellite industry started in the Netherlands. And I think that when our rover works on the moon, also the world will be different. And then it will be much easier to get the rover on the other landers and going to Mars, because it's so lightweight and so versatile. So I would say, if the rover wants to go to Mars, it has to perform on the moon. And when that happens, then Mars. So now it's making science fiction, working on the moon, will be going to Mars.
Yeah, exactly. And it's also nice to mention that Delphi C3 is also helping us a lot. So in my introduction talk of today, I said that we are trying to gear up the engineers of the next generation, also within the TU Delft. And so some could say, okay, but only the people within the team are actually working on this rover. But the Delphi C3 is like around 12 years ago, and they developed it for an even longer time. And we're still using documentation or like documentation to help us basically to work on this space mission. So I hope I have answered together with Chris this question.
Okay, thank you, Saviër. I think that we can give a word to Peter. I think that I'm really interested to know your opinion about our dreams to go to Mars.
Was that a question to me?
Yes, we answered a question about will you try to go to Mars next, and I wanted to ask your opinion about missions to Mars and our dreams about Mars.
Well, both Mars and the Moon are currently in the field of attention, and I do agree with the point that Chris made, is that if you manage to demonstrate this technology on the Moon, you'll be in a very good shape to actually demonstrate this on Mars. The lunar environment is far more complicated and dangerous, temperature, dust, radiation. So it's a complicated area to go to. So once you manage to get it working on the Moon, then Mars is easy in a certain way. But it's a long way to go. And currently the focus of the world is shifting towards the Moon. Now this can change quite rapidly. That's usually related to who's in control in a certain White House. But for the moment, your opportunity to actually piggyback towards the Moon is a lot bigger than going to Mars. And there is certainly a lot to do on the Moon still. So go to the Moon first, and Mars will follow afterwards.
Mm-hmm. Okay, thank you so much for your opinion. And we're going to the next questions. I think Nick can answer this question. It's really short and sounds sadly, it sounds like no system engineer team.
Yeah, so the original organization of the team had the systems engineers grouped into the operations team. So they were like a sub team within operations. But now moving forwards in 2 weeks with the restructure, all the systems engineers are going to be forming the systems engineering core, which is a more systems engineering focused team. So yeah.
Okay, thank you. One moment. According to the structure of our team, we have one more question. Where can I apply to join the team? Claudia, can you say something about this?
Yes, so if you want to apply to join the team, you should go to our website. It's just zebro.space. And there you can click on a tab, Join Us, where you can see all the open positions that we have. And then there is like a form you should fill in. And in that form, you also upload your CV. So I think that covers it. Yeah.
Yeah, absolutely agree. Yes, don't forget to apply. Maybe some of you will join us next time. And we go to the next question. It is, the question is, will you also discuss thermal management? Ufuktan, can you?
Yeah, so I didn't discuss it, but we will have a passive thermal system instead of active. Active thermal system weighs a lot, and we don't have the weight for it. So we will have passive thermal system. We will use multi-layer insulation, and by using different colors and changing the conductivity, we are now analyzing the operational time on the moon based on the temperature.
Thank you for your answer. Next question. At what angles to the sun can you walk? Can you walk towards the sun? Stijn, can you answer this question? Hello?
Yeah, hi. So we cannot walk towards the sun because the problem is that the shrimp cameras become too hot, and we can't see anything because the illumination of the sun is it's very high, and it means that we are gonna be totally blanked. That also that's the same for when we get into the shadow. The shadow is so dark that you can't see anything if you're become into the shadow and you're not pointed to a lighted spot. It becomes completely black and you don't see anything because on Earth there's like the shadows are very hard because on Earth there's some atmosphere where you have a little gradient of lighting, but on the moon this atmosphere is not there, so it's either dark or it's either light. If you talk about angles, yeah, the shrimp cameras can have a field of view of 45 degrees, so that would probably also the angles we can't walk towards the sun. Oh, Katya has left.
Okay. Interesting. No problem. I think I'm not sure where Katya is right now, but I also see the questions, so I will just continue. The next question is, how are you funding the launch and lift to the moon? I can answer that myself, actually. So that is something obviously not easy, but it is something that we're working on a lot, especially with the public relations department, of course. So we're working a lot with partners, trying to gather funds, but also a lot of partnerships, which are really valuable to us. And we have a close watch from the TU Delft. So yeah, there's not like a really short answer to that. It's like partnerships with everyone, with the TU Delft is the biggest one, actually. So for the next question I have, how are you testing the rover against moon's gravity?
Yeah, so we're gonna test the rover here on Earth by lifting it with a helium balloon, so it becomes the gravity on Earth is six times higher than on the moon. So a helium balloon will help us to get rid of most gravitational forces. We are also thinking about testing it with an arm holding the rover. And then you might think about lifting it up with a little spring or something. And we also want to test it. Want to test dropping the rover on Earth because of when we get deployed, we need to fall on the surface of the moon, and this is really important to test as well.
Yeah,
Okay.
I see that Katya is back, so I will.
Yes, I'm so sorry for some technical problems, but it's new space, and we are going to the moon not because it's easy. Okay, let's come back to questions. The next question is, what is the biggest obstacle for getting the zebra on the moon? I think that Ufuktan and Chris probably can answer this question.
I will divide this question into two parts: the technical and the non-technical answer. The obstacle, the biggest obstacle is like, in my opinion, surviving the launch and operating on the moon, which is very harsh. And for the non-technical answer, I would like to invite Chris to say something about that.
Yeah, you could think of several non-technical questions, like there is the Moon Treaty, legislation, licenses, and so on. But we have experienced that everybody from Agentschap Telecom to the ministry is very helpful in this. So actually, I don't think there are showstoppers there. So the biggest problem is the eternal problem. It's funding. There are many things that people can do in kind for you, but when you want to be on a rocket going to the moon and on a lander, you have to pay hard cash, and yeah, that is the biggest problem, I think, at the moment. Also, not a showstopper potentially, but at the moment it is maybe the biggest problem I face.
Okay. Thank you. And we have two more questions. And Raj, are you here? I think that you can answer these questions. We have two questions for you.
Okay. Let's go.
I will read them. What type of phenomena do you hope to detect with the Alpha swarms?
All right. So, so that question depends on the number of satellites in the Alpha swarms, and also the duration of the life of the network itself. So, if we have 10 satellites, for instance, and 10 antennas, therefore, we could make beautiful maps of the sky in the radio spectrum, and that's similar to the maps that I showed to you over a period of a year or so. But if we had 30 or 50 satellites, then we can actually do transient detection of Jupiter flares, for instance, or look at extrasolar planets, right? So those kind of things. But if we have 50, 100 satellites or so, then we can actually study cosmology in the purest form of things, in the sense that you can actually study epoch of reionization, the origins of the universe, what happened immediately after the Big Bang. And so that will be the most attractive questions, right? So these are some of the phenomena. It will depend on the scale or the size of the network itself.
Thank you for your answer. And the second question to you is, don't you need huge antennas for space-based radio astronomy? How can you do this with the CubeSats while on Earth we use huge parabolic antennas?
That is correct. So indeed, for many of the famous arrays on Earth, we use large dishes. The one in Netherlands, the Westerbork array, is 25 meters. GMRT is 35 meters. VLA is around 20, 25 meters again. These are huge dishes because they look at higher frequencies. At lower frequencies, the wavelengths are longer, which means that we can have much more simpler antennas, like a dipole antenna, which could just be a long sort of strand of metal in a way. Right, so that makes things much simpler. However, because they are long wavelengths, you also need really long antennas, and these could be some sort of a tape which can be rolled out from CubeSats, right? So a lot of studies in the last 2 decades have happened in Netherlands, starting with TU Delft about 15 years ago, where we looked at tape rollouts of dipole antennas, which can be used for Alpha science. Right? So I hope that answers the question.
Thank you. And thank you to all speakers for the answers. It was really interesting. And we have a question for our participants. Did you expect this? Yeah, we have a questions for our participants on Slido. It's a poll. Please rate the quality of our presentation. Give us a feedback. We need to know how can we make our presentations better. So please go to Slido and pass this poll. I also see on Slido. Yeah, I see it's not a question. It's like It's like a wish. Hi guys, nice presentation. I can't wait to see it happen and to assist you with the radio communication from Dwin Gilo. It's from Yanwar. I'm not sure that I can write this his last name correct. I'm so sorry for this. And yeah, I want to know about our pool. Did you pass it? Higher is better. I also will pass this poll to make a mark of our Mooninar. So yeah, I think that Peter, maybe you have some questions to ask to our speakers from Lunar Zebro or to our participants.
Well, I have a technical question to the team, if they don't mind. One of the first presentations, you highlighted the dangers of the lunar environment. You talked about temperature, the angle of the sun. What have you done so far on the risks that come with lunar dust that you can collect via charging or toppling? And they have a tendency to screw with your electronics and mechanisms. So how much have you looked into this so far?
Ufuktan, are you here? I think you're the perfect person for this question.
I think he's on the moon already. Maybe some, maybe some of another speakers.
I'll check. He should be next to me. Maybe if someone
Chris
else
can, maybe Chris can also answer this question. So, yeah, we still.
Oh, sorry, I was muted. So, what do you exactly want to know, Peter, of me?
Well, my question is, what have you looked at so far on the mitigation of the risk of lunar dust?
So we have done tests, for example, in India with the Indian Space Institute, where they have something that looks a lot like lunar dust. So it's sharp and abrasive. And we spent quite some time in keeping the bearings closed for this dust. And we also have been looking at a special coating that would make the solar panel so, how would you say, slippery or something like that, that the dust would easily slide off. But we also have been looking at nightmare pictures of the wheels of the lunar, the rover of Apollo. So we are still investigating that, but we are doing tests with material that is very much a lookalike.
Okay, thank you. Maybe Peter, you have another questions or no? Maybe you want to ask.
I have tons of questions. The moon has been a fascination for me for a long time. So let's see what comes into my mind shortly. I mean, so far I've seen it's great what you guys have been working on. I'm very impressed by it, and you probably guys were ahead with starting on this, and I think the tides are really changing when it comes to lunar exploration with the commercial lunar program coming up. So I reckon your shots of flying on a mission to the moon will become bigger faster than you probably know it. The US, you have a great many companies now starting on commercial services. Also, Europe is looking again, hopefully definitive this time, into a lunar lander. So your opportunities are looking good. One question that comes into mind, and I think if you've looked into it, considering the tilting capability of your solar panel, how eligible will your rover be for operations on the South Pole area? Because that is where I guess 90% of the landers will go when they start flying. So will your rover work in that low inclination, even extreme temperature region?
it was designed for that. The first plan, the first mission we had was actually that the rover would go there. So we did extreme temperature testing, even of the batteries, and also the fact that the solar panel can be tilted up till this 90 degrees. Everything has to do with the South Pole. So actually we had to think again about the rover if it would not go there.
Okay. Thank you so much for your questions and for your answers. And we have the last question during our webinar, but it's not the last question for us. The last question is, can I join as a part-time member? Maybe Saviër, can you answer?
Yes, definitely. So most of our team members are actually also studying. Yeah, so actually most of us are part-time members. So if you look at our website, you can actually see which positions are full-time and part-time. And the link is on the screen right now, if I'm not mistaken. So all the positions, they have some explanation, including the amount of hours that you will probably need to fulfill this position. So, yeah, if there are any questions about these positions, there is an email as well, email address on this website, which is publicrelations@zebro.space, which is on the slide again. Great. So you can send your question regarding a position there as well. And also, if you want to send an open application, that's also possible. You can send us your CV with a motivation letter to that same email address.
Thank you so much, Saviër. And okay, I want to remind you that you can ask our questions. You can ask your questions to us on our social media, via email, on our website, or you can do anything to ask a question. So thank you all so much for your attention, for our partners, for our webinar partners, especially to Netherlands Space Society, for this report, for supporting us, for supporting our webinar, and also thanks to our project partners. Without them, our project couldn't exist. And thanks again to webinar partners. Thanks again to our speakers. You have brilliant reports, and the tour was great. I'm missing these places. And thanks to our participants who watched us, who today became closer to the moon together with us. And I think that it's not the last time. And I think that we can make like a common screenshot with all speakers and say goodbye to our participants. Okay. Maybe can somebody make a screenshot? Common screenshot. I think we should make it all. Yeah.
Okay. 3, 2, 1.
Okay. Thank you so much. Okay. Stay in touch. Look for our up-to-dates and apply to our open positions. And see you next